I'm not just anybody. My love won't be taken down by a bullet, and I've tried everything, but I'm best at disappearing. And your love used to bring out the best in me, and now I'll be dying, and I am reminded, love to remind me that you're too cool to fall in love. You're too smooth to get caught up in something you can't walk away from. Walk away from. And I know it's safer to believe that you don't mean a thing.
Hi everyone. Next up we're going to have Nemanja Rakicevic from Google DeepMind. I hope you enjoy the talk and have fun.
Thanks. Thanks, Raquel. So yeah, my name is Nemanja and I'm a research scientist at Google DeepMind. And today I'm going to be presenting a paper done in collaboration with all these amazing people. And I'm going to talk about how we managed to make agents adaptive. So if you like the talk at the end, you can check out more information in our paper, Human Timescale Adaptation in an Open-Ended Task Space. Yeah, so what's the motivation behind our work? So currently, if you want to train an RL agent, you do it through backpropagation. So the whole training process takes a long time because you have to propagate the gradients. But so something we want as a crucial skill in the future, because we want to basically interact with the agents on a human time scale, we want them to also learn at the same scale, right? So how we tackle this problem is we used a transformer-based agent. So we used a pre-trained transformer, which was trained on a vast task distribution of 3D and embodied tasks. And I'm going to go into all these details later, so don't worry. And we used a meta-RL approach. And also, in order to make this approach more efficient, we had to employ curriculum learning, and we used distillation. All of this I will cover. So what are the kind of results we got in the end? We got agents that can adapt to environments and the environment dynamics they haven't seen during the training. And we call these agents adaptive agents, and short is ADA. And we also noticed some behaviors which emerged. Some of them is hypothesis-driven exploration. And then once agents manage to solve the problem, they further refine their skills to make them even more efficient. And one interesting thing we managed to see is that scaling laws also apply to RL and not just the large language models. So first things first, can I have a show of hands of people who have heard about reinforcement learning, or RL? Okay, seems like half-half. Okay, I'll just go like quickly, very short, high-level recap. So in RL, we usually have an agent, which is computer agent, robot, some algorithm, which kind of interacts with an environment. And it interacts by deciding on which actions to execute and executing them in the environment. And then at each time step, the environment gives some observation, which is basically kind of a state of the environment, and potentially a reward. And the goal of the agent is to maximize the reward. So how it works is basically the agent can try a sequence of different actions, which we call a trajectory. And some of them are going to be wrong, like reaching wrong part of the terrain or some other kind of useless state. Or it can reach a goal state, which will give a positive reward. And once this is reached, we try to assign credit to the sequence of actions which led to this reward. And that's kind of the main kind of point of RL. How do we do this credit assignment, and how do we then update our agent's model so it's better next time? So in deep RL, we use like a large neural network. So we do this through backprop, and that's how we improve the model. So then what is meta RL? So imagine we have this system I just explained, and then instead of one task, we actually sample from a distribution of tasks, and this could be seen as an inner loop and outer loop. So once you optimize the agent to kind of learn all these tasks, you have something which we call a meta RL problem. So this is like very high level. If you want to learn more, I'm happy to chat later. So once we have this, we have like a base to talk about. So in the next couple of slides, I'm going to show you what our agents actually do. So in the next reels, I'm going to show you a case of a single agent interacting with an environment. And it's basically interacting with an environment it hasn't seen before. So this is like completely new. It hasn't seen it during the training. And all the kind of decision it's making, it's not actually learning. So it doesn't get any, doesn't do any gradient updates. So it just uses dynamic memory. Just some kind of additional terminology. So basically, how we set up the problem is we have something we call an episode, and we have something which we call trials. So each episode can be consisting of multiple trials. And you can see this as like one episode being one task it has to solve, and this another. So you can imagine yourself playing a video game, and you can play it as many times as you want. It always restarts, but your kind of memory keeps, is persistent, and you kind of learn during this interaction. So that's exactly what we do here. So each episode, within the episode, we can restart the environment many times, but the agent's memory stays constant. While between episodes, we also reset the agent's memory. So this can be also the same version of the environment we had before or another environment. But basically, it's important to distinguish these kind of trials. And why is it important is because we want the agent to improve over trials. OK, so let's go to a concrete example. So our agent is the blue avatar, and it's in this kind of 3D environment. You can see there are many different components. There are different like landscape with different levels. There are some objects, and but the agent doesn't see all of this. It just sees a first-person view, so like an RGB image from a first-person perspective, right? So we give a goal to an agent, and in this case, the goal is given in a, let's say, symbolic language. Agent, hold, and an object, right? In this case, it's a black cube. But as you can see, there's no black cube in the environment. And this is intentional because we also add something called rules. And these rules are a way for the agent to interact and manipulate the environment so it can achieve its goal. And for example, one rule is that if black pyramid touches a yellow sphere, it will actually create the object it needs to achieve the goal, right? But then to make it, of course, a bit more complicated, we add also a distractor rule. In this case, it's called a dead end rule, because if you touch a purple pyramid with a yellow sphere, it actually disintegrates both objects. And then you cannot do the first one if you don't have enough objects. And that leads you to a dead end, because you cannot do anything until the environment restarts again. OK, so those are the kind of main components. One more thing to know is that for every trial, we give the agent 20 seconds to complete it, and it can consist of, for one episode, but it can consist of multiple trials, right? And it gets a reward of 1 if the goal is satisfied per time step. Okay, I hope more or less you got this. So I'm gonna show you now a video of agent doing this. So this is the environment I explained. So in the first trial, the agent just moves around, tries different things. and then it accidentally triggers the dead end rule, right? So you cannot basically complete a task. These two objects disappear, and it can just like play around, but nothing happens. And it just has to wait for the timer. Okay, so the next trial, now it actually manages to connect the proper objects. But it kind of takes some time until it finds it, tries with different ones, and finally connects them, and it holds. So it does this kind of victory dance, basically because it gets a reward per time step. And now in the final trial, it basically just knows directly what to do. Yeah, so it gets much more reward because it holds the objects for longer. Okay. That's the same one. Okay, so that was a single agent. So we can also now take more agents and put the same policy in and see what happens. So in this case, we have this game which is cooperative, so it's not competitive, so the agents have the same goal, which means even if one agent just fulfills it, both get rewards. We have the same rules, so don't worry about that, it's the same as before, but they're not known to the players, right? So they don't know these rules, so they have to figure them out. So let's look at this example. So initially, of course, they just wander around, explore, nothing happens. But then they figure out. But then they figure out some useful skills like throwing. But only one agent knows how to solve the game, right? And the other one gets the reward, but it didn't do anything. But then in the last trial, they actually cooperate. One brings one object, the other one brings the other one, and they actually solve the game cooperatively. So this completely emerged. We didn't like hard code this, anything. It's just based on a very, very large set of games, which we call Xland. So this is a set of procedurally generated terrains and basically task definitions, goals, rules. And there's, when you do it in this way, you can get 10 to the 40 different variants. But we just use a subset of this to train, and I'll show you how exactly later. But some of these games are very hard for humans to understand because this is not something that's maybe interesting. So we also handcrafted around 60 games inspired by some typical games, which we can actually evaluate agents on and see if there's something interesting going on. So just to show some results, so basically we compared the performance of our agents to humans. So what I'm showing here on the y-axis is the median score. So how we calculate the score is basically the reward it gets on the last trial, right? Because that's the one which actually matters. And x-axis shows how many trials it needs until it gets a certain reward. So basically that's case shots, that's how we call it. Cool, so basically one important, so we're evaluating on 30 held out tasks, which it hasn't seen during training, and also we employed a couple of expert human players and evaluate. But there is one thing to note, the response time of humans and agents is different, so when we normalize for this, the difference is less drastic, but it still shows that the agent is either better or on par with human players. So this is kind of the main takeaway from the kind of results section. If you're interested for more, please check the paper. But basically, one also thing to know is that during the training, of all of the training tasks, none of them had more than 6 trials allowed. So when you have an episode, you can try it only 3 times. But even if we continue during tests for more than 6 trials, we see that the performance keeps going up. Okay, so what is this method? This is going to be a bit technical, so we can chat more after if you're interested in certain parts. So basically, we're using a large-scale transformer-based RL algorithm with a curriculum. So let me unpack this. There are basically 4 main components. First component is this large-scale pool of training tasks. As I mentioned, we generate them procedurally. There are like, in the end, we used around 25 billion different tasks, and we sample from them. And of course, each task is basically like the task I showed you before. So the second component is the muesli-based RL agent, which has a transformer XL architecture. And the third component is this structure of like creating the episodes. So they consist of multiple trials, which is based on the RL squared paper. And the final one is the curriculum. So this is basically one of the also important parts, because we don't just uniformly or randomly sample from the big task distribution, but we actually select the task which give the agent some signal based on how well it performs on them. So if the agent doesn't perform well on any of them, we discard them. If it's too hard, right? Or if it's too easy, we also discard them. So we are looking for this Goldilocks zone. So those are the kind of like the method. And now I'm going to go through some of the components which actually made the biggest impact. And the biggest, of course, impact is just scale. So when we use the larger network, this had a very big impact. So here I'm showing you the score on the y-axis, and on the x-axis I'm showing the model size. So here it doesn't look like a big difference, but we're just evaluating zero-shot performance, right? So that's like we throw an agent in, we give it one trial, and that's it. But what happens if we increase the number of shots we evaluate it for? Then you can see the actual very significant difference. So for every multi-shot evaluation, we see that the difference is very large. Another thing that we evaluate, so this is a median score, right? So like average kind of over all the games, but we also want to focus on the percentile. So the 20th percentiles shows us the performance of the majority of the 80% of the games. The difference being, so these are not taking into account some outlier games that could kind of skew the results. And then here we actually see that if we just do one shot, there's almost no improvement. But as we improve, as we increase the size of the model and use it, evaluate for few shots, the improvement is there. Okay, next important thing is the context length. So context, I don't know if you're familiar with transformers. They are basically models which go over a sequence and apply certain attention to the sequence in order to make some kind of predictions or outputs. And the size of this sequence affects, of course, the performance, but also memory. So in our cases where we have multiple trials, so a larger history, we actually care about the context, right? So the larger the context, you can remember further information back in time. So what we tried is first seeing how it performs when we have very high number of trials, more than 24. So our baseline is just the basic model. It kind of tapers off after 24 trials. It kind of doesn't improve. But if we also add some trials in the training, which is the blue curve, that shows improvement. But if we also extend the memory, so that's the red curve, that again adds to another jump. So how we did this in short, basically we couldn't just increase the context naively, because that would require a lot of memory. So what we did, we applied some encoding of frames. So we basically summarize frames using a recurrent neural network and then feed that into the transformer. And the reason for this is it improves performance, but also it helps us with the memory consumption, because it's that super expensive. Okay, so that's regarding the number of trials, but if we also see the effective kind of time steps that the memory can kind of attend to, we can also see that there's a boost in performance there. So the larger the memory, we see the higher performance, especially significant when there are more trials involved. Okay, so it's both for median and 20th percentile. Cool. Okay, next thing which might be interesting as well is the actual architecture we used. So the original Muesli paper uses RNNs. So they don't perform very well when we kind of show them, allow evaluation of multiple trials. But then we tried to add attention to RNNs, and that gave us a significant boost. And then, of course, if we try exactly proper transformers, that gave us another shift, right? So that's a very important component, so the architecture of the model. Okay, so now the curriculum. This is the fun part. So how does this work? So once we sample when we train the agent, we train it on certain tasks, right? So this curriculum actually selects the tasks from this enormous Xland kind of set of tasks that we really want to use for training. And how it does this, so first we uniformly sample like a set of episodes that can be different lengths, different number of trials, etc. And then we run it through a no-op filter. So how that works, we run 10 episodes of each task with a no-op agent, which is literally an agent which doesn't do anything, right? It just sits in the middle. And then we see, okay, if this agent gets some reward, it means the task is too easy. It's something like, okay, I'm standing here, the black cube drops in front of me, and I'm already like getting rewards. So that's not interesting because the agent doesn't get any like pressure to improve. But then again, we use our best agent we have so far, and if it kind of, so we discard all those tasks which are too easy. But then the tasks which are not too easy, we run our current training agent on it, and see how that performs. Of course, if it's too hard, we also discard it. But if it's too easy, we kind of discard it. But we just want this kind of Goldilocks zone, which kind of gives us some improvement. Cool. So how does that work? That's pretty cool, but it still has some limitations because it's a bit inefficient, as it uses only the returns. So you have to wait until the end of the episode. So one other thing we implemented is the prioritized level replay. So that's more like kind of in the evolutionary literature, taking inspiration from the evolutionary literature, as it uses the fitness score that the agent gets on the task. So this fitness score is can be anything. Can be something like some internal metrics, like how well the agent predicts some actions, what's the TD error, which is like something very typical for RL. And we just basically figure out that we can only run the episode one time, and that also gives us a way to kind of classify the tasks which go into the training pool. So to see some like performance kind of gains from this kind of approach, we can see that if you just uniformly sample, we don't get any improvements, but if you do any kind of filtering, especially PLR, we get like a significant improvement. And then that begs the question, so how does this affect memory? Because we have to evaluate 10 times the agent on a task, and we're not using this for training, right? Because we can discard them. But actually, we can see that if we plot the flops, which is the compute on the x-axis, and the score on the y-axis, we can see that these approaches are actually more efficient than uniform sampling. And okay, so those are kind of scores and performance, but what does it actually do? Why is it so better? And what we can do, we can actually take this training distribution and analyze it. And we can see some of the features of the environment, such as the number of hidden rules, the number of trials, etc. And we can see how that evolves over time. So what I'm showing here is when we take all the tasks in the environment, check this feature, number of rules, and average it. So this shows this number. And then the dotted line is another test set we have, so the one we created by hand, inspired by like real interpretable games. And the red dashed line is our test set, which is a held out set. And then these two, the blue and the teal line, they show no-op filtering and PLR. So what this tells us is basically we get some kind of a curriculum. We kind of start the agent with something easy, so like very little rules, like basic stuff. And then we increase the complexity, right? And then we increase to the average being of almost 1.5 rules per task, right? Which is even more than we have in our hand author set. We can also do this for other kind of features, like number of rules. And we can see also there's this kind of curriculum going. For number of trials, it's not very kind of obvious that there's a curriculum, but basically PLR enforces longer, I mean like more number of shots for the agent to train on. And the number of dead end rules, that's also like a very important thing. As you can see there is kind of a curriculum going on, and we want it to be higher. Cool. So that's the curriculum. What about the number of tasks and the task complexity? So that's also an interesting thing, which we couldn't like get from that analysis, but we can see that if we take like an empty room, we say this is like the most simple task, right? There's like very little complexity, but if we add some like landscape, like more complex levels, that's something which is much more complex. So why is this important? So if we, on the x-axis, show the size of the model, so like from 6 million parameters to 75 or 57 million, we can see that in the top row, where we have like super simple tasks, the score improves with the number of trials, but at some point it starts dropping. And it kind of, if you see, there's like, it almost reaches like 95% of the score, so the success rate. But the reason for this is basically there's no need for larger models because it's kind of, we're not using their kind of expressive capabilities. But if we train on more complex tasks, then it actually makes sense to use larger models. And of course, the difference is more obvious when you look at the 20th percentile. Okay, so what about the number of training tasks? So the size of the training set we train the model on. So of course, there's a big difference there as well. So you can see what we're showing here. The line with the circle on it is agent train on a smaller set, and with a triangle is on a larger set. The difference in colors is the size of the models, right? So more or less it's similar. We see that there is a difference in the score when we train on a larger set of 25 billion tasks, as opposed to training on only 200 million tasks, especially in the larger models. But this difference becomes even more obvious if you look at the 20th percentile, where this difference is much larger. So basically, the conclusion is, of course, we should train on more tasks as we then get more diverse tasks, so the agent can build up its experience. Okay, so finally, a very important component is also distillation. So the concept of distillation, it's very well known in the literature. It's basically when you have a teacher or a neural network, and you're trying to kind of distill its knowledge to another network. In our case, we have a teacher agent, which is trained for 25 billion frames. Let's say our budget is 100 billion frames, right? So instead of training every time from scratch, which can take months, we trained one teacher agent on 25 billion frames, and then use this to kickstart the training of the student. And then we do this only for 4 billion frames, and then continue training normally. So why do we do this? There are 3 reasons. This accelerates research because we get to iterate much faster, as this 4 billion is like just a fraction of like the total budget. Then the still agents actually get to be better than the teachers. And finally, this enables scaling because we can then use smaller models to then kickstart larger models. So what does this mean actually? So if this is our kind of training time on the x-axis and the score on the y-axis, so in teal, you see the teacher, right? So if we start teaching the teacher, and it kind of learns to some extent to like 25 billion frames, and then we freeze the weights and kickstart the training of the student. We do this by modifying its loss function to add a KL term, so to try to mimic the actions of the teacher, and we continue training the other teacher, right? And what we see here for these 4 billion frames, the speed at which the student reaches like 50% of the rewards is much faster than what the teacher got in like almost 20 billion frames. And then as we continue the training, we can see that the student actually reaches this higher performance than what the teacher did. And this is even more pronounced in the 20th percentile. So that's something which is very important and like saves us a lot of time to play around with other cool stuff. And what it means that it enables scaling. So basically what we do, if we train from scratch, for example, a large model in blue or a small model in teal, we see that they don't, like the large model doesn't perform that well, but we get some performance with a smaller model. But then if we use the smaller model to kickstart another small model or another large model, then we see that actually the colors invert. So the larger model has a lot of benefit from this, and we get the best performance in this way. So yeah, we get quicker and higher performance, but also like in the kind of in the asymptotic setting. Cool. Yeah, and the same for the 20th percentile. Okay, and the last kind of important component is actually humans that help adapt the agents. So what we can do, because we have multiple trials, we can just input a demonstration from a human into the first trial and then actually let the agent continue from there. And we can see if we don't do this in the T line, basically the agent has like certain performance. But if we skip that first trial and input the kind of humans demonstration, which knows how to solve the task, then we get like much better performance. Of course, it's not perfect as the human would do because they know the task. So yeah, that's kind of the numbers. But how it actually looks on a certain example, if we have an agent in this kind of two-room situation where it has the goal is to reach the yellow cube. So what it will do, it will randomly select to go on the first trial either in the upper or lower room. Let's say it goes to the wrong side. It will probably do a couple of trials in that room before going down. But what the human demonstration can help it with is just go straight forward to the yellow one, and basically the agent then continues from there in the subsequent trial. Okay, so those are kind of the most impactful components. And to sum up, of course, I know this is a lot to take in, but yeah, I'm free if you want to chat later. So basically what we learned from this, the key takeaways, is that if we train RL agents on large scale, which means like on a very large number of tasks, we get something like a foundation model which exhibits certain capabilities on control problems, such as in-context adaptation, scaling laws, and even this emergent collaboration, which happened in the multi-agent situation, right? And finally, some of the most important components here are the attention-based memory that we get when we use transformers, and the autocurricula, which helps us efficiently select tasks which are actually useful for the agent. So going from here, we can ask ourselves, okay, so what are the kind of next steps which are lacking? So first of all, the environments we generated are procedurally generated by us, but like computer, but like we kind of set up the rules. But that inherently carries some biases, right? So like we decide what are the range of the rules, what are the range of the environments, etc. But we would actually want something which can be generated in a more kind of creative way, so we get even more diversity. And also, where do the rewards come from? So for now, they come from roles, right? So from goals, which again we decide, we give like the ranges, etc. But I think it's more scalable if we can actually learn these kind of reward functions, as that would generalize even over a larger kind of set of tasks and environments. So one kind of step towards this was recently published by my colleagues at DeepMind, some of them who I worked with on the previous project. It's called Genie. So how Genie works, it's actually training a very large model on a vast distribution of games and videos, but in such a way so you can create avatars or agents which are controllable by humans by keyboard, for example. And what this actually ends up giving us is a promptable model which you can prompt, and it generates this environment and you can just play in it, and it's super cool. So yeah, these are some of the examples, but like if you're interested, you can check out their blog and paper. It just came out maybe a month ago, so yeah, that's super cool. So that would be kind of the end of my presentation. Hope you found it interesting, and yeah, I just want to thank everybody for your attention, and also my colleagues who I worked on this. And yeah, please check out the paper.
Thank you, Nemanja, for the wonderful keynote. And now we're going to have a couple questions. So if you have a question, just raise your hand. And do we have any questions? Yeah, we have one there.
You showed that in some cases increasing the number of parameters actually like worsen the model's performance. Is that something that you can explain or not?
Yeah, I guess for that case where we have like simple environments, so it's all about how you use the parameters. What are they used for? So if you don't give enough like data, for example, the model can overfit, and then all these additional parameters don't do anything useful, and can even maybe learn some like spurious correlations, and even kind of something that's not useful for the task. So I don't know exactly what would be kind of the reason in this case, but those are some kind of typical reasons why it happens, like overfitting, basically, when you have a more complex model than the task.
Okay, thank you.
Next question. Yeah.
Hi. When you showed the tests with the human demonstrations,
Yeah.
Did you also test them with the held out scenarios? So did the training with the human demonstration help the other non-train the validation scenarios?
Just to try to repeat if I understood,
Yeah.
did we, when we evaluated with humans,
Yeah.
did we use the test set or the hand-created set that we made? Or
Any of those scenarios, but for example, you use a model which was trained with the help of humans, and then did you try to see if that model could, on its own, be better than the than the other models that weren't trained with humans?
Okay, so we didn't train any models with humans. That
Okay.
thing I showed, maybe I can show the slide. Okay, yeah. So there was this when we prompt the first trial, we give a demonstration. Is that what you mean? Or yeah. So that's actually, there's no like that's just using the memory. So it's not getting any. Yeah, this one, right? So when we do this, it actually doesn't use the subsequent trial to kind of backpropagate. All of these things I showed, they don't learn anything during the trials. It's just we freeze the weights and we just evaluate them, right? And that's the beauty of this thing, right? Because they don't need to we don't need to fine tune them on new environments. They just like do trial and error, this kind of hypothesis driven exploration, and they learn how to solve the task, right? So there's no like backpropagation there.
So the human help is only helpful for that scenario.
Yeah, this is just to like see how it affects. Yeah.
Thank you.
We'll just take one last question if there's any. Okay. After just after this session, Nemanja will be out back to answer, to chat with you and answer any further questions you may have. And now we're gonna pick the winner for this session. Miguel Miranda. Congratulations. Congrats. Okay, another round of applause for Nemanja. Amazing, amazing, thank you. It was very, very informative. Thanks.